Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY212, we are at the lecture number 16 and the topic is the initial value problem. By the initial value problem, we mean that if some initial value of wave function are given to us, then how we can find the any value at some later time t. In quantum mechanics, this we can do with the help of Schrödinger equation. So the idea is that if we have some initial state which is given to us, consider it like psi, which is a function of position, and time is 0, which means that we are at the initial time. Now if this is a wave function of any quantum mechanical system, for example a single particle like an electron, so you can think of it like electron is sitting somewhere and not moving, and at that time this wave function is given to us. Now our goal is to find out that what would be the final state or any state at later time, that is psi of RT. So the solution of initial value problem is to find out the psi RT from psi R0, where t is equal to 0 means that it is the initial time. This t is equal to 0 we have taken for the simplicity, otherwise you can take any time and you call it t is equal to 0, or you call it the initial value. Now if this initial value is known to us, then how we can find this psi RT, which is some value at some later point. This we will do by with the help of the time dependent Schrödinger equation. So in time dependent Schrödinger equation, we know that we have this form where H is the Hamiltonian. This we have already learned when we were learning about the Schrödinger equation. So this is the Hamiltonian, which can be time dependent and which can be time independent. Now in order to find out the solve the initial value problem, what we will do, that we will construct new operators. You know that this H is an operator, a Hamiltonian operator. So now we will construct new operators out of this H. We will call them the functions of operators, and these functions of operators will help us to solve the initial value problem. So how we do this, that we, by exponentiating the H hat, which is the Hamiltonian, construct a new function. This u is a new function, which is a new operator, which is a function of this old operator H hat. So a function of an operator is also an operator. So u is an operator and it is a unitary operator. By unitary operators we mean that these are those operators which will give us real values. In coming lectures we will talk about them in more detail. So for our calculations we will also need the inverse of this unitary operators, or this functions of operators H. So we construct them in this way, and what we will do in the procedure, that we will use this u minus 1 as an integrating factor for Schrödinger equation. So in mathematics you learn that you solve some equations using the help of integrating factors. So these functions of operators and these new operators will be treated like integrating factors. So let's start solving the initial value problem, but before that also keep in mind that these functions can be expanded in Taylor series, where you can see the first term, leading term, is independent of the operator H, and then we have a first order of operator H and the second order, and so on. So whenever we have this type of expansion, we say that we introduce the effects order by order. So in leading order we have zero order effect, which means that H raised to power 0 is equal to 1. So there are no quantum effects involved here. But in the first order correction we have this H order 1 and so on. So as we increase upon the orders or extra terms, we keep on correcting. But in most cases we will only need this second term up till second term or the first corrections, and this will be enough to solve the real value problems or to get the real values. So this is the Taylor expansion of our this integrating factor or the operator which is constructed out of this operator H. So in order to solve now the Schrödinger equation to get the initial value problem, what we will do that multiply this Schrödinger equation, that is time dependent Schrödinger equation, from the left with this u. It is important to understand that the multiplication from the left is necessary, because if you multiply from the right, then these operators are not sometimes commutative, which means applying this operator first and second this gives us different results. So therefore we will multiply it from the left, and after this multiplication, the Schrödinger equation will become this one. Now in order to understand that how it comes here, you can apply this time derivative over in square brackets thing, and there are two terms. So if you apply the derivative on the first term first, then what you will get, that you will get this exponential back, and then the after the second term you get the time derivative, so you will get h bar by h psi. So this will give you the first term over here in this equation, and when you will directly apply the psi this derivative with respect to time, you will get the second term or the term on the right hand side, because this u is actually this thing. So if you put the u inverse is this thing, if you put the u inverse value over here and this bring it to the other side and make it equal to 0, so you will get this equation. So what we have done, that we have combined these two terms into a single term and taken out the derivative, and when we apply the derivative, it gives us back the both of the terms over here. So we can go from this step back to this step by applying the time derivative. It will give us both the terms. Okay, but why we put this into this form? Because we want to integrate and we want to find out the value of psi. Now the integration becomes simple, and when we integrate this in the interval, let's say 0 to t, what we get is this form, because now integration is gone, because there was a time derivative. So time derivative cancelled the integration, and when we put the limit, because we have integrated it into this interval that is between 0 and t, and when we put these limits, because we will substitute the integral is over d by dt, that is dt. So in place of t we will substitute 0 and t, and when we put 0 over here, this will give us the initial value wave function. So this, you see, now we have brought in the initial value of wave function, and this is by somehow will be known to us. If psi of or 0 is known to us, this is the definition of the initial value problem, because if it is known to us, we can find out psi. But still this is not in a good form, because psi is not taken out, but we can take it out by multiplying this with the if we multiply this equation with the u, which is the inverse of this, this will give us the desired result, because if you multiply with the u, this will be cancelled out from here, but you will get u with here, which is -1, and this equation. Now you know that if I have psi initial value over here, and I calculate this operator acting on it, I will get the final value or value at any desired point. And here we have assumed that u and u minus 1 are inverse to each other, by which we mean that if you have u and u minus 1, they are inverse to each other, and this will give us identity operator. So when we multiplied with this u, then in this first term we have applied this this fact that u and u minus 1 are inverse of each other, and when multiplied together, they will give us an identity operator. And this is the initial value equation, where you now know especially this first part over here, this first part, because if we know this initial value and applying this, sometimes we call it a time evolution operator. So this time evolution operator will evolve this initial value into the time, and as it is evolved, it will capture the dynamics and will give us this psi. So this time evolution operator in quantum mechanics is a very important operator, which is acting on any kind of wave function at starting point will give us the wave function at the later time. So the two wave functions are connected by this the time evolution operator. Now we turn to the examples of it, and we say the eigenvalues. If we choose the solution to be the eigenvalue of h, because h is an operator, and if we consider that this is the eigenvalue of h, then we know that the initial value psi r0, let's denote it by phi n, because there are discrete set of the eigenvalues. So let's call the initial values as phi n. Then the time independent Schrödinger equation becomes like this, because this phi n is, as you can see now, is the initial value wave function, and when h acting on it will give us the set of eigenvalues, that is discrete eigenvalues phi n. And we also know that there are corresponding oscillatory solutions as well. So if we put back this into the equation we found on the previous slide, so what we will get, that instead of psi r0 we will put over here phi n, and instead of h bar, because this is connected, this h hat is connected by the Schrödinger equation with the En, so we can replace this with the En over here. So this you can see En here, but this En is also related to the omega n. So we can put this equal to omega n over here, and you can see that this we can find out the eigenvalues with the help of the eigenvalues of h. If we say that this En are the eigenvalues of h, this solution in terms of the frequencies, this is the oscillatory part, and then you can see the dependent part, time independent part is connected to the discrete eigen function of the operator h. Okay, so after making this discrete eigenvalues out of the initial value problem, we go towards the stationary states. That is a very important concept in the quantum mechanics of the stationary states, and you will see that it somehow comes out of the initial value problem. So consider that we have a system and it has an eigenstate of the Hamiltonian at t is equal to 0. That is the initial value thing. So we want to calculate the expectation value of any operator, and as you know that the expectation value of any operator is defined by psi star a hat psi. So this is the initial value, this is at the initial value at t is equal to 0. That's why we have used psi r0 and psi star r0, and as we have used different symbol for it now in terms of the discrete set, this is phi n star and phi n. So we have now defined the expectation value of any operator connected to any observable at t is equal to 0. So what will be the value of this expectation value of any observable at a later time? We can calculate this, and if we calculate this by this definition, that instead of putting psi r is equal to 0, we put psi rt. So it is the same definition as we have used over here. Instead t is equal to 0, it is only t, and here this is phi n star equal to phi n. So now we want to know how this second equality comes about. There is a simple calculations involved over here, and you can see that if psi n as we have already calculated is equal to e raised to power minus omega n t phi n, then the if we put into here this definition of psi, this En will be taken out of the integral, because it does not depend on the position, it's only the time part, it's the integral on our position. It will be taken out and will be cancelled out, and then you can see that this at is equal to this thing as we have used in the previous slide. So so now we find out that at any solution, any expectation at t is equal to 0 is equal to the solution at a later time. So it means that the states are stationary and they are not changing, because what we have found at t is equal to 0 is exactly equal to at later time t. So this is the condition for the stationary states. So in some systems, for example, you can think of an electron revolving into the around the nucleus. It will not change its state and time is passing on, so we call that these are the stationary states. So sometimes the concept of stationary states is used in the quantum mechanics to represent any physical system. So in today's lecture, we have seen that in quantum mechanics, the initial value problem can be solved with the help of Schrödinger equation. And when we take the initial value of the wave function, then we put it into the Schrödinger equation and we connect it to the wave function at the later time with the help of time evolution operator. So whenever time evolution operator acts on the some wave function at any time, let's call it initial time, then it converts it into the wave function at later time. So this is a very important concept in order to understand the dynamics of quantum mechanical system. Thank you very much.